Multilinear models can fit large datasets with many predictors. But the relationship between predictor and target isn't always linear. Look at, for example, the plot I have there. The data points are in blue circles, and we're trying to fit it with a linear model. It's obviously that's not the correct model. What we want is to fit a model that is not linear. So y is equal to f of x given some parameters beta. So the equation we have is y is equal to f beta of x. Now the simplest nonlinear model we can consider for a response y and a predictor x is a polynomial model of degree m. Y is equal to beta 0 plus beta 1x plus beta 2x squared all the way to beta m xm. Just in the case of linear regression with cross terms, polynomial regression is a special case of linear regression. We treat each x to some power m as a separate predictor. Those we can write the design matrix, and we start with the design matrix of a polynomial regression. Every column here is the predictor to some power, and compare it to the multilinear regression design matrix, which each column corresponds to one predictor. What we can see is that if we turn every column of the polynomial design matrix into a different predictor, we can use the same methodology we use for the multilinear regression. Let's go step by step. Given a data set x1, y1, all the way to xn, yn, we write down the equations. Y is equal to beta 0 plus beta 1x, all the way to beta m to xm. First, we're going to transform the data by adding new predictors. So my x tilted, the new predictor, will be 1, x tilted 1, x tilted 2, all the way to x tilted m. Now x tilted k is the predictor to some power k. Now we can find the coefficients for each polynomial degree by minimizing the MSE using vector calculus, as we have shown in the multilinear regression. Now beta hat will be x tilted transpose, x tilted, the whole thing inverse, times x tilted transpose times y. Fitting a polynomial model requires choosing a degree. Let's see 3 examples. On the very left, we fit the data with a linear model. On the very right, we fit the data with a polynomial up to degree 50. And in the middle, we fit it with degree 2. Now on the left, what we see is called underfitting. The degree is too low, and the model cannot fit the trend. On the very right, we have what is called overfitting. When the degree is too high, the model fits all the noisy data points. What we want is a model that fits the trend and ignores the noise. Now, high degree of polynomials lead to overfitting. That will be the subject of the following few lectures. There's one more thing we need to consider before we actually model data. Do we need to scale our features for polynomial regression? Now, linear regression is invariant underscaling. What do I mean by that? It means that if we multiply x by some number lambda, then the resulting coefficients will be scaled by 1 over lambda. Also, the MSE will remain identical. In other words, we don't have to scale. However, if the range of x is small or large, then we're going to run into some troubles. Consider a polynomial degree of 20, and the maximum or minimum value of any predictor is large or small. Those numbers to the 20th power would be problematic. That means that we're either going to have overflow or underflow in our data. So it is always a good idea to scale our predictors when considering polynomial regression. We have 2 ways of scale our data. One is called standardization, and the other called normalization. Standardization is subtracting the mean of the values of the predictor and divide by the standard deviation. And normalization is subtracting the minimum value of the predictor and divide by the range of the predictor. Scalar has a method to do that. It's called standard scalar, which can be used in order to scale the data before we do polynomial regression.